Welcome to Online Algebra 2. This is section 5-5, Theorems about roots of polynomial equations. In this section, our objective is to solve equations using the Rational Root Theorem, the Conjugate Root Theorem, and then we are going to use something called Descartes' rule of signs. And basically what we're going to be doing in this section is we're going to be going through a bunch of stuff that is going to help us factor something that we can't factor with some of the techniques that we used in the last section, like quadratic techniques, factoring out the GCF, the difference of perfect squares, the sum and difference of perfect cubes. So those sort of techniques are all great to factor something. But what we're going to be doing in the next section is factoring things that none of those techniques work. So in this section, we're going to go through a couple of tricks that are going to help us in our pursuit of factoring polynomials that are more difficult. And the first thing that we need to know is that the factors of the numbers of the leading coefficient and the constant term, right, the first term and the last term, can help you factor the polynomial and solve my equation p of x is equal to 0. Find the zeros, find the roots. Okay? So, basically what we're going to be doing is to find the roots of the polynomial equation, we are going to guess and then check to see if it works using synthetic division. Okay? This is not efficient, right? This is inefficient unless there's a way to to minimize the number of guesses or the possible roots. And there's a theorem that helps us do that, and it's called the Rational Root Theorem. And the way it works is something like this. So suppose you have a polynomial with integer coefficients. There are a limited number of possible real roots, okay, real roots of that polynomial, p of x is equal to 0. So the integer roots must be factors of the last term. Okay? The other roots, the rational roots, have a reduced form of p over q, where p is a factor of the last term and q is a factor of the leading coefficient. So what does that mean? It means that every factor, every possible factor of this polynomial is going to be a factor of that term divided by a factor of that term. And since 1 is a factor of everything, right, if we just have these factors divided by 1, those are the integer roots. These factors divided by everything else are all the other rational roots. So if we look at this quick example, here's my constant term. Here's my leading coefficient. The answers, and we would never factor it like this, but the answers must be a factor of 10 divided by a factor of 21. Well, 2 and 5 are factors of 10. 3 and 7 are factors of 21. And so the roots are negative. So the factors, right, positive or negative, plus or minus for all of these. So basically, if I'm gonna write down every single possible factor of this quadratic right here, it would be all of these over 1, all of these over 3, all of these over 7, and all of these over 21. So there could actually be a lot of them to check. Okay, let's try a problem. Okay, the factors of 2 are plus or minus 1, plus or minus 2, right? Because 1 times positive 2 is 2. Negative 1 times negative 2 is also 2. The factors of 5 are plus or minus 1, plus or minus 5. Okay, so the rational roots of this polynomial are going to be these 2 over 1, and then these 2 over 2. So that means that my rational roots are plus or minus 1, plus or minus 5, both of these over 1, which I don't have to write, and then plus or minus 1 again, right? Or sorry, a plus or minus 1/2, and then plus or minus 5 over 2. 1 and 5 over 1, 1 and 5 over 2. Now, there are 8 of them, right, plus or minus. So there's 8 numbers here. If I were trying to factor this, and I can tell already that it won't factor by grouping, if I'm going to try to factor this expression, I am going to start with these 8 numbers. And in fact, I'm really going to start with those 4 because they are easier to do than the fractions. Okay? And then, once we get one of them to work, then we can use other techniques in order to factor the rest. Let's try that again. Okay? What are the rational roots of this polynomial? So here we have plus or minus 1, plus or minus 3. 8 is -8, but it doesn't matter. It's always going to be plus or minus. 1, 2, 4, 8. All the factors of 8. 1 times 8, 2 times 4. So we're going to take all 4 of these. So my answer is plus or minus 1, 2, 4, 8. All 4 of these over 1. And then all 4 of these over 3. 2/3, 4/3, and 8/3. So the numerator is always going to be 1, 2, 4, 8. 1, 2, 4, 8. All over 1, which I don't have to write. All over 3. The 3 is not a factor of 8, so it never appears in the numerator. Okay? And again, instead of just guessing any random thing to try to factor out of this expression, to try to say this could be a root, I now have 16 choices, still a lot. But again, I would start with these first 4, 8, and try those first. And then once you find one root, we're going to use synthetic division to factor the rest of the polynomial. And we're going to continue finding roots and dividing out things until we have a second degree polynomial. And then we are either going to factor it or use the quadratic formula. Let's actually see how we are going to do this. So what are the roots, the rational roots of this polynomial? Okay, let's find out. So here we have plus or minus 1, plus or minus 3, 5, and 15. And here is just 1 and 2. So my rational roots are plus or minus 1, 2, both of these over 1, both of those over 3, both of those over 5, and plus or minus 1 over 15 and 2 over 15. Again, these two are always going to go in the numerator. Okay, so if I want to find out what the actual roots are, not the these are all the ones that are possible. Now I have to find the actual ones. I'm going to guess one of them, any of them. Right, so there's 2, 4, 6, 8, 16. There's 16. So I'm going to guess one of these 16 numbers, or plus or minus. I'm going to guess one of these 16 numbers and say, I think this one is going to work. And I'm going to test it either by plugging it into X and seeing if I get 0, or using synthetic division. Let's do that method. I'm going to guess 1 is going to work. This first root. Okay, 15, negative 32, 3, and 2. Am I missing any variables? 3, 2, 1, no. So I don't need a leading 0, or I'm missing 0. Right? Remember synthetic division. The first step is to bring down the 15. Multiply. 15 minus 32 is negative 17. Multiply. And I can already tell that this is not going to give me a 0. That's what I'm looking for. I'm looking for a 0 right there. I didn't get a 0. That means positive 1 is not a rational root. Okay, well, that's nice. Let's try the next one, negative 1. And I kind of like to go in order and do these in a very methodical way. So 15, negative 15. These are going to give me a huge number, and I'm never going to get down to 0. Okay, so I can just say that that's not going to work. Okay, let's try 2. So bring down the 15. Now I get 30. That's negative 2, negative 4, negative 1, negative 2, and I get a 0 at the end. That means that 2 is one of the rational roots. And remember what this resulting thing here down here means is that my expression is now 15x squared minus 2x minus 1 equal to 0, right? Not because of this, but because of this right here, right? This is just the remainder. The degree has gone down by 1 because I've divided out a linear term, right? I divided out x minus 2. Okay, that is one of the factors. Now, this can factor, right? The factors of 15 times negative 1, that's subtracting, give me 2, are 3x, 5x, with the negative going with the 5, and the 1 right there, which means x is 1/3 and negative 1/5. So there are my three answers, 1/3, negative 1/5, and 2. And notice that they are all listed in my possible rational roots. Okay. Now, for the purpose of this course, right, usually one of the integer coefficients or one of the integer terms will work for your first attempt. Right? I don't want you to have to try guessing some of the fractional ones. That makes it much more difficult. Let's try this one. Again. So, what are my possibles? 1 and 2, 1, 2, 3, and 6. So we have plus or minus 1, plus or minus 2, 3, 6, all over 1, and then a half. Now, this would be 2 over 2, which is 1, which I already have a 1, so I don't need to write it again. Okay, so I can skip that 1. 3 over 2, and then 6 over 2, right? 6 over 2 is 3. I already have 3, so I can skip that one again. So these are the only possibles right here. So only 12. Again, guess what I'm going to start with? All right, 2, 1, negative 7, negative 6. Synthetic division. Not gonna work this time. Okay, let's try a negative 1. That would be a negative 2 there then. And this would give me negative 1, positive 1, negative 6, positive 6, and that one works. Okay, and again, remember what this means, 2x squared minus x minus 6, and we can now try to factor this, guess and check method. I want the, let's go 3 and 2, with the 4 being negative and the 3 being positive. Okay, and so that makes my three answers negative 1, negative 3 over 2, and a positive 2, all of which are listed in my possible rational zeros. Now, there could be other zeros that are not on that list that could be answers, like irrational numbers, like radicals, like imaginary numbers, but this list is going to be just give me the basics, the possible rational roots. Okay. Speaking of irrational and imaginary numbers, If you remember from 4.8, that complex numbers come in conjugate pairs. A plus bi and a minus bi are conjugates. The first term is the same, the second term is different. This applies to irrational numbers as well. A plus radical b and a minus radical b are called conjugates. Because of primarily the way the quadratic formula works, right, that we have negative b plus or minus this radical, b squared minus 4ac over 2a. Because of this, and that we have this whole radical here, when we have a complex number or an irrational number that is a root of a polynomial, its conjugate is also going to be a root. So if you have this one, you must have this one. So if we have a rational, right, coefficients, right, all they have to do is rational. We're not really going to use imaginary anyway, imaginary coefficients in a polynomial. But if you get a plus b, then you're also going to get a minus b as a root. Okay, they're going to occur in conjugate pairs. And the same thing, if you get an imaginary root, you're going to get its conjugate as a root as well. So that means a quartic, fourth degree, right, quartic, the quartic polynomial has rational coefficients. If radical 2 and 1 plus I are the roots, what are the other two roots? So we know it has 4 roots. Okay? So if this is 1 and this is 1, this is the other, right? There is no non-radical part, so it's 0 plus radical 2. 0 minus radical 2 is the other one. This is my fourth one, 1 minus I. So 1 plus I is a root, 1 minus I is a root. Cubic polynomial, if this is a root, 3 minus 2i, this must be a root. Okay. This is not a radical. It's not an imaginary number. I only have 3 roots, 1, 2, 3. There they are. Okay, so just because you have 5 over 2 as a root doesn't mean you have negative 5 over 2. In fact, if you look at the problems that we did back here, right, we got 2 as a root. That doesn't mean we got negative 2. No, we got a third and a fifth, or negative, but okay. So just because we have this 5 over 2, it doesn't mean that that tells us anything else. This one does tell us something. It tells us that if we have 3 minus 2i, we must have 3 plus 2i. That also means that we can build polynomials even though we're not given all of the roots. So a third degree polynomial with rational coefficients so that it has a root of negative 4 and 2i. And just looking at these 4 choices right here, I can't really pick it out, right? I don't see exactly what those 2 roots have to do with this, and I don't want to factor all of them. So what I'm going to do is I'm going to take the factors that gave me those roots. So if my root is negative 4, that means my factor is x plus 4. If my root is 2i, that's x minus 2i. And if I have 2i, I also have to have that one. Third degree, 3 roots. So that's x plus 2i. Now all I have to do is multiply these together. Now, I would highly suggest multiplying the conjugates together first. Because if you do the first 2, right, you're going to have some i's flying around in there. You're going to have all sorts of weird stuff happening. But when you multiply these 2, you get x squared plus 2xi, weird, but minus 2xi, and they cancel out. And then last, remember, negative times positive gives you a negative 4 I squared, but I squared is equal to negative 1, so my expression simplifies to x squared plus 4. Okay, then I just multiply these two together. X to the third first. Let's just do these two, plus 4x squared, keep it in order, plus 4x plus 16, and I can see that my answer would be C. Okay, let's try it again. This is much harder. Okay, why is this one harder? Because now my roots are 2 minus 3i and 2 plus 3i, a binomial conjugate pair. My other two roots are 8 and 2. Okay, so if I'm going to make this polynomial, we're going to need some room for this. Okay, my first terms is x minus 8, then x minus 2. And remember the way I'm getting that. I'm saying that x is equal to 8. I want my factor equal to 0, so I subtract the 8 from both sides, and I get x minus 8. Okay, if x is equal to 2 minus 3i, and I want my factor equal to 0, I have to subtract and add these to both sides. So my factor turns into x minus 2 plus 3i, and its conjugate is still x minus, this one's the same, x minus 2 minus 3i. Okay? Now, we'll do these two. We'll do the easy one first, and then we'll do these two. You want to multiply the conjugates together, no matter what, because you want the i's to cancel out. This is going to be a minute. So we got x squared minus 8 minus 2. That's 10x plus 16. Okay. When you multiply a trinomial times a trinomial, you get 9 terms. Of those 9 terms, anything with an I will cancel or simplify. Okay? So, x squared, x times minus 2, minus 2x, x times minus 3i, that's minus 3xi. Weird, we're not going to worry about it because it's going to go away. To the negative 2, we distribute the negative 2. So that's negative 2x. To this one, positive 4, negative 2, plus 6i. Okay, again, we have an I in there. We're not going to worry about it because we know eventually it's going to go away. That's what happens with the conjugates. So plus 3xi, okay, that's good, minus 6i. And then these last terms, remember, it's negative 9i squared, which turns into positive 9. Okay, negative and positive, 3xi, 6i, and there. Okay, and so now we have x squared, 10x plus 16, x squared, negative 2x, minus 4x, and 4 and 9 give me my 13. Now we just have regular numbers to multiply a trinomial times a trinomial by and get 9 more terms, that some of which are going to combine. So now we get x to the fourth. When I distribute the x squared across all these, minus 4x to the third plus 13x squared minus 10x to the third. Right, now we're here, plus 40x squared and minus 130x. Here we have a positive 16x squared. I'm running out of room here. 16 times 4 is 64. So it's a minus 64x. And my last term, 16 times 13, is 208. Okay. Combine like terms. X to the fourth. We got an x to the third there. We got an x to the third there. That's it. So that's minus 14 x to the third, x squared, x squared, x squared. So that's 13 plus 40 plus 16 gives me a positive 69x squared. And then 130 and 64 give me a negative 194x plus 208. So, not necessarily simple, okay? But as long as we do the first step right, getting all the roots, we'll eventually get to the answer if we are careful. And again, the hardest part is multiplying the two imaginary conjugates when they're binomials. Much simpler when they're when they're trinomials. Much simpler when they're binomials. All right, so that was two theorems so far. The Rational Root Theorem and the Conjugate Root Theorem. The next theorem was made by this guy, René Descartes. You might recognize him from philosophy. I think, therefore I am. You might recognize him from the name of the thing that we graph on, right? The coordinate plane that we graph on is called the Cartesian coordinate system. Cartesian after Descartes. So he really came up with analytic geometry and a lot of stuff inside algebra having to do with that. And in the course of his studies, he realized there was a connection between the possible number of positive or negative roots and the signs in the standard form of the equation. And this is how it works. This one's a little weird, okay? So the number of positive real roots in your original expression is either equal to the number of sign changes between consecutive coefficients or is less than that by an even number until you run out of. So if there's two sign changes, it could be 2 or 0 positive real roots, right? You just keep subtracting by 2's until you run out of room. To find so that's positive real roots. To find the number of negative real roots, we need to analyze p of negative x, okay? So what that means is instead of x in the polynomial, we plug in negative x, which has the effect of changing the sign of everything that has an odd exponent to it. And we'll go through this in a second. Okay? And again, it's the number of sign changes or less than that by an even number. Okay? And in both cases, multiple roots count twice, right, according to their multiplicity. So here's my expression. Let me write this down. F of x is equal to x to the third minus x squared plus 1. Okay? So for the possible positive, okay, possible, not how many there actually are, okay, but this is the possible number of positive real roots, okay, is going to be the number of times as you move from left to right on this polynomial, how many times the sign changes. Well, it starts positive, right? I don't write a positive, but it starts positive. So that's 1 change, 2 changes. So there could be 2 or 0 possible positive real roots. So that means if I were to factor this, I could get 2 real roots that are positive or 0 real roots that are positive. Okay. The next thing I have to do is analyze f of negative x. That means for every term, I switch it to a negative x. Negative to the third power is a negative. Negative squared is positive, but then this negative is still there. And then this is just a 1. Okay, so what that has the effect of, when you analyze f of negative x, what you're doing is you're changing the sign of every odd exponent. This one's odd, it changes. This one's even, it stays the same. This one's even, it's x to the 0 power. It stays the same. Okay, now you can see that there's only one sign change. So that means that the possible negative real roots, there's only going to be one. So here's the, again, this is a weird theorem. The benefit is that now if I'm guessing rational roots, I know that there could be a positive one, but I know there has to be a negative one. So if I'm going to guess, right, if I'm going to guess roots here, it's going to be plus or minus 1. I'm going to go with negative 1 first, just because negative 1 has to work, because I know there's a positive real number. And I also know that conjugate roots have to come in pairs, or irrational roots have to come in pairs. So if I try negative 1 on this, 1, negative 1, don't forget the 0 for x, 0, 1, and bring down the 1. All right, well, 1, negative 1, 0, positive 1, 2, positive 2, 2. So that didn't work either. Okay, so negative 1 is unfortunately not going to work, but whatever number that I do get, whatever fraction I did get, so it's not a rational number. It's going to be a it's going to be something else. I'm going to actually see what that is. Let's try another one, though with Descartes' rule of signs. So what does Descartes' rule of signs tell you here? So 2x to the fourth minus x to the third plus 3x squared minus 1 has 1, 2, 3 sign changes. So it's 3 or 1 positive, and then I'm going to change the sign of every odd exponent. So this one changes to positive, this one stays the same, and this one stays the same as well. So there's one negative real root. So there's 3 or 1 that are positive, and there's 1 negative. So again, the point of this section was less about solving the different equations, and it's more about using a few of the theorems to help us better understand what is going on inside of the theorem and how we can solve it and how we can extract a lot more information from it. And in the next section, we put all of this together in order to answer many, many, many questions about specific polynomials. Okay. So real quick, just 4 and 5 real quick. If your polynomial functions are 5, or the zeros are 5 and 9, that's it. There's only 2. If they're these two, there are 3, because you also have minus 2i. Okay. And that is 5-5, theorems about roots of polynomial equations.